Okay, can you see the document, the file on simple circuit applications and differential equations?
Yes, Miss.
Okay, thank you. So what you have here will be the simple circuit applications regarding the use of differential equations in modeling circuits that may contain the circuit elements that I'm going to discuss first in here as an introduction. So the three circuit elements that will be present in your circuits later on, I'm sure you're very well familiar of this because you are EE students, will be the resistors, the inductors, and we have the capacitors. Now, since we only are limited to using first order differential equations to model circuits, so we will only take two at a time of this particular circuit element. So meaning we will not have all three circuit elements present in your circuit, because if that is the case, you will have a higher order differential equation. And if that is the case, class, you won't know yet how to evaluate such, because that's our next lesson. So the differential equations that you will be exposed to in a few minutes will be first order differential equations only. And as such, we will limit our circuits to RL, RC circuits. So RL circuits, meaning what you have there are resistors and inductors, or you have a resistor and an inductor. RC circuit, you have a resistor and a capacitor. Okay, we will not have, as I've said already, we will not have a circuit where all three will be present, because that would be now a higher order differential equation for their mathematical model. So for a resistor, I have here placed illustrations, pictures of resistors, and I'm sure you have seen this already in your lab. They have different colors there on the resistor and has something to do with their capacity. But anyways, these are how they look like in reality. And these resistors, when placed in terms of a schematic diagram or written in the schematic diagram, are written in this manner. Okay? Physics already told you that this is how it's represented in the circuit. So in this resistor, current I, most of the time I is represented as capital letter I, but once written in the circuit, it's just written as small I. You can use capital I or small I as long as you properly define your representation. Now, so this current I will be passing this particular circuit element, which is our resistor, and in the process, we'll have a corresponding, there will be a corresponding voltage drop in this particular resistor element. That particular voltage drop is the product of the resistance and the current. Now, we have the voltage here having the unit volts, the resistance having the unit ohms with this symbol, and the current having the unit amperes, so represented as capital letter A. So these are the things that you need to know regarding the resistor. As for the inductor, this is how they look like. Okay. And in the circuit, this is how they are drawn. So you have this one, the inductor, and you have the current passing through such an inductor as represented by I sub capital letter L. Now, if the voltage drop across your resistor is presented by the product of R and I, the voltage drop across your capacitor, your inductor rather, not your capacitor, will be the product of its inductance in Henry or Henrys and the rate of change of the current with respect to time. So now you have here the presence of the derivative already. And as such, when we write the model DE for this particular circuit element later on, you will have what we call a differential equation because of the presence of the derivative. So you have here a new constant, which is what we call as the inductance, unit of which is Henrys. Now, all our time unit when we do circuit analysis will be in seconds or should be in seconds. And most of the time, class, these seconds unit are, if given a certain quantity or a specific quantity in the circuit, would be either micro or milli or something like that. So you have to really express it in the unit seconds using the appropriate exponential equivalent of such. So I will be showing it to you later when we go to a specific sample problem. Now, with our inductor, your voltage drop will be 0. So if the voltage drop is 0, the inductor here acts like a short circuit. So it acts like a short circuit when there is no voltage drop across your inductor, because it is said to be that the current in such a circuit is a DC current. Now, DC current are said to be constant. And we know that if something is a constant and we differentiate it against another or with respect to another, the derivative of a constant is 0. So meaning this di dt here that we have will be 0 because it's a constant in the case of a DC circuit. So if it's di dt being 0, this one would be also L times 0, giving us no voltage drop across your inductor because it acts as a or like a short circuit. So I think you know also that when we speak of DC circuits, we have the battery as our source, whereas AC, it's like the manner of distributing power and electricity in our homes and industries. So most of the time, it's the AC current. Okay, but if it's just the battery, which is the source, then we have what we call as the DC current. Now, the third circuit element are the capacitors, and this is how they look like. They also have colors. And in here, associated with the capacitor, we have what we call its charge. And the charge of a capacitor is the product of its capacitance in farad and the voltage drop across it. Okay, so that is your charge in your capacitor. So charge here has a unit in coulombs. And mentioned a while ago, your capacitance has the unit farad. Voltage is still represented as V with the unit volts. Now, related to the charge of your capacitor is the rate of change of that particular charge. So the current that passes through your capacitor is expressed in terms of this rate of change of your charge with respect to time. Now, since the current now is in terms of a derivative or written in the form of a derivative, then that brings about a model equation, which is a differential equation also. So the rate of your change of your current, the rate of change of the charge, which has the unit column, then will be divided by seconds because it's dq dt here. So coulomb over second will give you the unit ampere. That's for the current. So now your current would be represented in another way as well. So take note, class, in here your current is represented by dq dt, the rate of change of its charge with respect to time. It could also be represented in terms of its capacitance, as you could see in here. Q is equal to CV. So it could also be represented in terms of its capacitance and the rate of change of the voltage with respect to time. So current is the rate of change of the voltage with respect to time times the capacitance. That would be now the current of your circuit. Now, why do we have this, Miss Ali? Why do we have here CV in the first place? We got it in here because I is dq dt. The Q in here, you replace by CV. So you place CV here. And since we know as a rule that whenever we have a constant, we don't differentiate it. It's written before the differentiation, and it's only the variable that we differentiate. So capacitance is a constant, so you have C, and now we have differentiated voltage with respect to time. Okay, so this rate of change of your voltage with respect to time, of course, will have volts over seconds as its resulting unit. Okay, so these are your added information regarding your capacitor. The charge, which is CV, and the current, which is dq dt. And if you use this one, you will have it also equal to C dV dt. In the inductor, you have a case of a voltage drop across it equal to 0 if your inductor acts like a short circuit or when your current is constant. It's a DC current. Now, we also have a scenario here in your capacitor when I is equal to 0. So now your capacitor acts like an open circuit. So rather than having a closed circuit, now your capacitor acts like an open circuit. And this is in the case wherein now your voltage is constant. Again, on the premise class that if voltage is constant and you get the derivative of a constant with respect to time, this will be 0. So if this is 0, you multiply it to C, of course, current will be equivalent to 0. We go back to our main equation for the current, which is this. And then we substitute it in here. And then we substitute dV dt equal to 0 because, as I've said already, it's written here, voltage is a constant. So there's no derivative for that case because it's a constant. So current is equal to 0. So our circuits now, our circuit application will only be limited to these two kinds of circuits, the RL and the RC circuit. Now, if your electromotive force or you have a constant voltage here, it would be easier to handle than having an electromotive force expressed in terms of the sine function or the cosine function in which the independent variable is time. Nonetheless, we will be discussing that also in the succeeding examples. But for now, before I go to any of the examples that are also present in this document, do you have any question in this part? I'll go up here, in here. So regarding your inductor and this one, your resistor. Do you have any question with these three before we go to the sample problems? You may write on the chat box if there are questions. Okay, I think there is no question. There are no questions because no questions were here on the chat box, so we'll proceed then. So before we go to our sample problems, we need to know the basic equations available for us to use to model our circuit. So the first one is the RL circuit. This is RL, that's not KL, RL circuit. And this particular model differential equation is taken from the Kirchhoff's voltage law, which says that the sum of the voltages in your circuit elements, in all your circuit elements, if you all sum it up, it should be equal to 0. So it's equated to 0, and the resulting model D in this case now is this one class for your inductor. Now, when you solve a problem later on, because there will be sample problems here wherein some formulas are already pre-derived for you to use, just like we have a pre-derived formula then in growth and decay. And we did also a pre-derived formula for Newton's law of cooling. We had also that, and we also had one for heat transfer. So in the case of the formulas that will be derived for you later, if you think those formulas are already applicable for the given problem that is for you to be solved, there's no need for you to start with the model DE. Okay, you need not start with this, but rather go straight to that formula which you think you can use in solving your problem. So in this particular model differential equation, this is for the RC circuit, you have the rate of change of the current with respect to time added to R over L times the I, and we have it equated to E over L. So E is the EMF, short for electromotive force. Your R is the resistance, L is the inductance. So your unknown function in this DE now is the current. Okay, it's the current. Your independent variable is the time. Now, this E could be a constant if we have a DC circuit, or it could be a function of sine and cosine if we have an AC circuit. But this is for your model differential equation for the RL circuit. For the RC circuit, your derivative is not anymore expressed in terms of I with respect to time, but this time it's Q with respect to time. The charge, the rate of change of the charge in your capacitor at any time t. And as such, your Q here this time is your unknown function. And your constants are at all the times your resistance and your capacitance. And this E, just like the E in here, could be a constant or could be a function of the sine and the cosine. In both of these differential equations class, if your E is a constant, this is converted into one form of a differential equation. If your E is a function of the sine and cosine, it is really this particular form of the DE that you will evaluate if there's a need for you to evaluate starting from the DE. Now, having said that, do you know what type of differential equations do we have here in these two? What type of DE are these two? Oh, linear. Thank you for that, Elaine. So you have a linear DE. So if this EMF is a function of sine and cosine, you really have to evaluate this DE using the technique for evaluating such. And it is, for recall, what is it that you need to know if you have a linear DE? What is it that you need to determine first? Linear DE, for you to be able to evaluate it. Review of your first order DE. Let's say this is a first order linear differential equation. The integrating factor. Thank you. The integrating factor, Gian, that's correct. So you need to determine the integrating factor. So review. If we have the integrating factor, anybody who can tell me what's the integrating factor of a differential equation, first order and linear? What's the integrating factor? Okay, sorry about that. What is our integrating factor? Somebody wrote here E, integration of P of X dx. Okay, Elaine, thank you for this. So in this case, class, if this is your linear DE, this is your derivative. This one is used in determining your integrating factor. So we know that integrating factor, just like what Elaine is saying, is E raised to the integral of, you're used to having it represented by P of X. Then, because your independent variable is X, now it's time. So we write here P of T dt. So in this case, your integrating factor will be the R over the L multiplied to the differential of T. And then you just evaluate because this R and this L are constants anyhow. So you will just have a case of E raised to R over L times the time because you will integrate the dt. Okay? Now, this is your P of T and this is your Q of T. Okay? Now, in this particular DE, if your electromotive force again is a function of sine and cosine, it's not a constant. The same thing, this is your derivative, and this one you will use for your integrating factor. So in this case, your integrating factor will be E raised to the integral of dt all over RC, which gives you an E raised to T over RC. Now, this one is your Q of T. What happens if this E is a constant? Just like what I've mentioned a while ago, you can convert this differential equation into a simple separable differential equation. Okay? You can do that. If you want still to have it evaluated using the linear approach, it's okay, class. There's nothing wrong with really sticking to the way it's written as linear. But it can be simplified to separable DE if you want to. As long as this E, as I have said, is E, constant. Now, do you have any question? Okay, there are no questions. Then we will proceed with the sample problem below. So what you have here is a source-free circuit. It doesn't have any source. And if we're going to use the Kirchhoff's voltage law, then we will not have any EMF to add to these two voltage drops. So we only took the sum of the voltage drop in your inductor and in your resistor. No EMF to be added to this because it's always class that the right side is equated to 0. So this is a source-free RL circuit. So no source. Now, a while ago, we discussed that the voltage drop across your inductor is represented by L di dt. It was shown to you. And the voltage drop across your resistor is Ri. Okay, then this would be equated to 0. What is good about this DE is not only is the right side a constant, but it is 0. So it can be converted into a separable differential equation. So if you're going to do separation of variables, you may transfer this one in here on the other side, and you multiply the entire dE by dt and divide by I. So what do I mean by that? You can transfer, so I'll write it in here. So you have di dt on the left, then you will have negative R over L times I on the right. Then you can switch this to, so you have di over I equal to negative RL dt. Okay, this is the thing that you're seeing here. So this one, which is negative, was just transferred here on the left side, making it positive again. If you will integrate this and supply the limits right away, so your initial current, most of the time, class, is represented as capital I sub O, and your current at any time t is I. And you will have here, of course, initial time is 0, and time at any time is t. So you will have an answer here, which is an ln. And if you will supply the limits, you will have I over I sub O, because the answer here actually is ln of I. And if you substitute the two limits, it would be something like this, ln of I over I sub O. On the right side, you will have, sorry, wait class, let's see. Okay, on the right side, what you will be having is negative R over L times time. If you wish to get rid of the ln here, you may use these expressions in the left and the right side of the equation as the argument or the exponent of an exponential function. So if you will have this as e raised to ln, you get rid of the e raised to ln. And what you have is I over I sub O equal to, of course, this would be e raised to negative R over L times the time. Okay? And you can cross multiply the initial current. So you have I, the current at any time t being equal to I sub O, E raised to negative R over L times the time. This is your ready-made formula for the current in an RL circuit. Okay, we refer to this as the instantaneous current. So if the problem gives you the specific value of the current, the initial current, you substitute it in here. And then, of course, the problem will give you also the corresponding resistance and inductance. And if it's sought by the problem to determine the current at a particular time, then just substitute the time as well. Of course, your resulting unit will be in amperes. So this is your ready-made formula. If this formula you think is applicable to the given problem provided for you to process, then you can use it directly without having to start with this DE. Okay? Any question? Any question? Okay, I think there's none. So there's a need for me to clear my markings here. So I can go down. So in that is the case, okay, in here it's being explained that instead of using C for the arbitrary constant, we use K, because here in circuit application, we talk of the C as the capacitance. So to avoid confusion and later on substituting the wrong value. But nonetheless, this is our concern, that I is equal to IO e raised to negative R over L times the time. Okay, I have given the formula already. We have derived the formula, but nonetheless, it's here. Okay, we represent the initial current as I sub O, and that's for time equal to 0. Now, we call this, as I have mentioned already, we call this the transient response, or this is your transient current in your circuit. The natural or transient response of your RL circuit is given by this formula. Now, related to your RL circuit is the concept of the tau. Okay, I'll go up. The tau, which is actually the reciprocal of R over L here, because it's L over R already. The inductance over resistance is equal to time. So it's the time constant of your RL circuit. And what is the significance or the essence of this time constant of your RL circuit? So it's said to be the time it takes for the current, the initial current, that is, to drop to 36.8% of its initial value. I think it would be best explained using the graph that is shown to you in here. Let me just, enlarge it. So you can see here the graph of the behavior of the current in your RL circuit over time. So if we increase time, this current decreases exponentially. So this is an exponential curve given by this exponential function here. And there is said to be a decrease because as we increase time, I decreases. So there's an exponential decrease or an exponential decay of your current. If it's ano class, if it's exponential increase, it would be something like this. Okay, that is exponential increase, but in this case is exponential decrease. So this is our curve. Now going back to the, let me clear my drawings. Going back to the concept of the tau. So if you have this as the initial current, time equal to 0, so this is your I sub O. The time it would take for this initial value of the current, whatever that is, to go down to 36.8% of this same value is tau. So it will take tau time for your initial current to decrease to this much of value. Okay, so you can see here 0.368 IO, meaning it's 36.8% of the initial current. When will this be? When it's time equal to tau. Okay, so that's the significance of this one. Okay, so far any questions? So you can use this formula directly whenever you are given an RL circuit, and all you have to do is determine values which you think this formula could be used to process such. Any question here? Okay, so no question. The reason why I did not have this recorded is you might have questions and you will not ask me about those questions. So I'm now willing to listen to questions if there are any. Okay, I think there's none. So let's say specifically now for the RL circuit that we have derived the transient response above. This is our equation. You're given that your current initially at time equal to 0 is 2 amperes. And you are to find an expression for I sub L valid for t greater than 0. So when you speak of find an expression class, it's asking for a formula. Oh, yes, an equation. And now, second requirement is you have to find its value at time equal to 200 microseconds. So these are the values of the inductance, and this is the value of the resistance. Okay, so we go back to our formula. This is our transient response. So if we substitute 2 for the initial current class, this is, I highlighted this one, this is already the expression that is being asked. What is the expression of the transient response of that particular circuit? So when you're asked for an expression, you are not to give a quantity, a specific quantity. Expression meaning it's a mathematical expression. Okay? Now, if specifically we are to determine the current after 200 microseconds, this is what I mentioned a while ago, micro should be represented properly in terms of its equivalent in exponential form. So it's times 10 raised to negative 6. If milli is negative 3. Nano is negative 9, and so on and so forth. So your time unit here, when you substitute for t, should be in seconds. So it's 200 times 10 raised to negative 6 seconds. Not that you will substitute the 200 microsecond original given value for time. Now, in this case, your answer will be a small current with a value of 0.8987 amperes. Now, since you are answering here in decimal, you may want to convert it into a higher value wherein you have a whole number. Then you convert your amperes to milliamperes, which needs you to multiply this original answer by 1,000. Why? Because you have 1,000 milliamperes to 1 ampere. So now you have 898.7 milliamperes for our RL circuit here. For this specific RL circuit, which is said to be source free. Wala siya voltage. Okay? Wala siya voltage source. Now, any question? Okay, sige. Now, what if you're given this time an RL circuit which has an EMF of 5 volts? 5 volts, a resistance of 50 ohms, and an inductance of 1 Henry. And this time, no initial current. So you find the current in the circuit at any time t. Whenever you're asked for this, find the current at any time t, your answer will be in a form of an expression. It should not be a quantity because it's at any time t. So meaning it is able to calculate for the current given the time. So the given informations were written here: EMF of 5, resistance of 50 ohms, and inductance of 1 Henry. And we went back to the DE, the original DE. This is your original DE. Okay? Now, you may ask, Miss, how can I convert this to separable DE? You can convert this to separable DE, but you may stick to the linear treatment. Now, how do you go about converting to separable? Just to show you, and we will discuss the linear process at the bottom part there. So you can transfer this 50I on the other side. So what is left here is di dt on the left. You transfer the 50I on the right, so that would be 5 minus 50I. Now you could see that there's something common with the 5 and the 50, and that's the 5. So you can place 5 times 1 minus 10I. Okay? You may keep the 5 in here or you may transfer it in here. It doesn't matter. You will end up with the same answer. So since this is an expression class which has the I, and this is also DI, you may place it here as a divisor and DT transferred here. So what I mean is this: you have a DI over 1 minus 10I, and you have here this 5. So you have 5 DT. So easier than if you're going to use the linear approach. Then again, the same thing. You substitute the appropriate values on your limit. So it says here, no initial current. So meaning this is 0 and this is I. And here you have time initial is 0 and then you have time t. And you can do the process of evaluation. I'm sure you know how to evaluate. This will yield an ln provided that you place here a negative 10 and you have a negative 1 over 10 outside. Okay, so you have negative 1 over 10 rather, ln of, if you will substitute the current I at any time t and the current 0 at time equal to 0, or that's your initial current, you will have an answer of 1 minus 10I. No divisor anymore because anyway, this will be 0. 1 minus 0 is still 1. So we have this. On the right side, you have 5t. Now, if you wish to transfer this again in here, you can have ln of 1 minus 10I, and you have this negative 1 over 10 if transferred here by multiplying both sides by negative 10 will be making the right side negative 50t. The same approach as we did when we evaluated for the transient response and came up with the formula. You will have this E ln of, or E raised to ln of 1 minus 10I. This will also be E raised to negative 50I. So you will have 1 minus 10I. Okay, place here the E. This is E is equal to E raised to negative 50I. I want an expression for the current, right? So the problem asked me for the current. So I will transfer it here, this one in here, and then do like this. It's just like I've changed the left side to the right to the left. What do I mean? So you will have this one here and this one here, and then interchange the two. Please interrupt me if you cannot follow, or you may raise your concern later. So I will write 10I is equal to, 1 minus E raised to negative 50t. I want the I, so that's the formula that I want. So the current I at any time t is equal to, I divide this entire equation by 10. So I have 1 over 10 times 1 minus E raised to negative 50E. This is how you do your evaluation for this original linear informed first order differential equation changed to separable differential equation. But if you intend to solve it using linear approach, of course, there's a need for you to determine the integrating factor. And this is where the E raised to negative 50t came into the picture. Okay? So, dira na siya naghalin ang integrating factor concept. And you have this. Isn't this one the same as this as well? So, if you convert your linear first order DE to separable, is not as cumbersome. If you're going to ask my opinion, but maybe you feel like you'd like to use linear, it's okay. It's not as cumbersome if you treat it as linear. However, class, in this scenario, if you have here, for example, in the initial 5, big example, initial 5 sine 10t. You cannot convert it anymore to separable. It can only be solved using linear approach because this time your Q of t is already a function of t. A function of t, not a constant. It's only doable to convert linear to separable if the right side of your DE is a constant. More so if it's a 0, it's even simpler. Okay, easier to handle. Now, before I discuss what's written here below, do you have any questions? Harap pa kamuda, class. Basi natulugan na kamuda. I understand that this is one very sleepy time. What if be missed if ang voltage ng inductor or resistance ang given instead of the EMF of the RL circuit? If it's the voltage resistor, sorry miss. Okay. If it's the voltage drop na constant, wala na tadi. Elaine, kung ihatag na sa imo nga value, get wala ka na di. Kay dira na mahalin ang derivative mo. So ang imo lang ang aton na diya scenario nga hindi siya constant, nag-vary siya. Kay di ba kung mag-constant ang aton nga ano nga voltage, ano pang aton di kay pwede mo na mala na pang suma total dira, wala na kinahanglan di. Kung ano pagid siya, kung capacitor pagid siya be nga constant ang voltage, wala na gid ta di kay ang derivatives ng voltage mo zero. So amo na siya. Okay? I hope that answers. So hindi gina siya matabo nga kung di ang atong istoryahan, tagaan ka na nga daan voltage ang duwa kay wala ka na sang DE, di mo na need ang DE actually. Ini siya when the need arise only. This quantity, negative 1 over 10 e raised to negative 50t, in this formula for the I, is called the transient current. Okay? You recall a while ago in the RL circuit wherein we don't have voltage. It's an open, rather it's a source-free circuit. So we don't have voltage. I mentioned that the transient response is also the transient current because of this, the exponential function. So in here now, if you have the voltage source, we have already the voltage here, the EMF value of which is 5. We have two terms which are having significance stand-alone. Sibla siya lang, maka-answer siya kung ano ang ginapamangkot. So ano na siyang pamangkot. So if you would be asked for the transient current, this is the transient current. Okay? And if you are asked for this particular problem, the transient current, you just need to substitute the time in here, and that would be your transient current. Now, why? Why it's called the transient current? Now, the reasoning is in here. Since this quantity goes to zero or dies out as t approaches infinity. So the transient current is that particular current which goes or has a value equal to zero as t approaches infinity. So substitute infinity here, e raised to negative infinity is zero. So it seems like it has no value whatsoever. It goes to zero or dies out as t approaches infinity. I like to go back to the graph so you can apply critical thinking there. Can you see this one? Your transient current will have a value of zero as t approaches infinity, meaning if we prolong this one, this I will not have any value because it's right on the horizontal axis. Okay, that's the significance of this one. It's transient because it dies out or goes to zero as t approaches infinity. What about this one? It stands alone also. It's constant. It has nothing to do with this first term. So the quantity 1 over 10 is your current, I, is called the steady state current. Steady state lang siya mo, miski mag-inano pa da ang time, amo gina siya yung iya value. Di gina siya mag-change to 1 over t. So this is called the steady state current. So in one expression, you get to answer two separate questions. That is, if you know the significance of the two terms that appears on the right side of your equation. And that is the transient current and the steady state current. Now, as t approaches infinity, the current I approaches the value of the steady state current. So if we prolong for this particular circuit, this circuit that is given to us, hindi amo ni nga circuit yaha ang kay base ma-confuse ka mo. Kay hindi amo na yung nga circuit. Ang ini nga circuit. So for this circuit that we're talking about, as t approaches infinity, since this one dies out, your steady state current will be 1 over t. So your current for the circuit will be approaching the value 1 over 10, which is the steady state current. Steady state in the sense, class nga, hindi gina siya mag-change t approaching infinity, meaning forever and ever, amo na siya ang current sa imo circuit. Because ini siya, wala na epekto, nag-zero na siya. It dies out.